Hi everyone, welcome back to our channel. In today's tutorial, we are going to build something, a very powerful tool. This tool can read your PDFs in your local computer and answer questions from them like a human expert. This technique is called Retrieval Augmented Generation technique, and in short, we can call this as RAG. You'll find this application in many enterprise level AI apps like legal document search and or while creating virtual research assistants or when you are creating some internal knowledge bots, etc. You name it. This is a very critical application, many enterprise level AI applications. So let's quickly understand how this bot works actually. For example, if you type a question, what is CMF? It will take some time for thinking and it will give you some answer and also some of the sources from where this bot derived this answer. So as far as the provided context indicates, CMF stands for the cumulative mass function. Yes, this is what is expected, but one key understanding is this answer is not coming from the main LLM. This answer is coming from these PDFs actually. These PDFs I have saved in my local directory and I have trained this bot on those PDFs. So whenever you see an answer, so this answer is mainly coming from that PDFs actually. For example, if you give any different question like what is XML, it will take a while to think and so it is saying I don't have enough information to answer your question about XML based on the provided context, because though these are randomly taken but they are mainly related to Python and machine learning. There is no instance of XML in these files. So that's why you have got an answer like this actually. So in this tutorial, we will see how we have created this bot and we will go through every detail in creating this kind of bot based on LLM, large language models. So before going ahead, first let's understand what RAG is, Retrieval Augmented Generation. Let's understand what it is. You see, when you ask a question to any regular large language models like ChatGPT or DeepSeek or Claude or something, if you ask a question that is there in your local document, the ChatGPT or your large language model cannot answer it because it does not know your local document, right? Even if it answers something, that answer was mainly from the knowledge it was trained on, not from the explicit PDF that was there in your local directory. So if your question is about a PDF on your computer, the model has zero idea about it. That's where this RAG comes in. It connects your question with your private data. It searches the PDF first, pulls out the relevant information, and then asks the language model to answer using that info that was retrieved from the PDFs actually. In short, this RAG bot searches your local document first and then generates an answer based on it. So why use this RAG in the first place? So many LLMs like GPT-4, etc. are very powerful, but they are not all-knowing bots, right? So they don't know your company's internal processes. They cannot access recent events or private files in your companies. And most importantly, they hallucinate, meaning they confidently make up facts. They create some illusionary stories. RAG solves these kind of limitations by injecting live relevant information directly into the model's input, and we don't need any retraining for this. In this entire RAG workflow, so it involves some key steps actually. First one is user query, document chunking, embedding the chunks, storing and searching the vector database, prompt construction, and finally generating answer using the LLM. So let's go through each of this step in detail. It all starts with the user query. For example, if you ask something like what is the warranty period for this device? So maybe the device can be a phone, but if you ask something like this, the answer for this question can be anywhere in the your local documents, right? If you have local documents, maybe 1 to 100 documents, the answer may exist in your first document or the answer may exist in your 99th document. We cannot tell actually. And the crazy thing is, if we search by keywords, we can never be able to find the answer because the exact keywords like warranty period or device may not be the right answer for this question. So we have to search based on the meaning actually. Once we have this question in place, then what we have to do is we have to chunk all the documents that we have into some small and manageable chunks. meaning you can think of these chunks as a few sentences or a small paragraph. Why this chunking is necessary? Because LLMs like GPT or some other have strict limits. We cannot just feed them the entire PDF in one go. It's too much for it to digest. So we have to chunk the entire PDF, each PDF into some smaller pieces of information. Once we chunk this, next we have to embed the words into some sort of numerical vectors. So this process is called embedding. These are all some of the embedding models that are available. So the first one is Almini LM, L6V2, and the second one is BGE small n, text embedding 3 small. The last one is OpenAI one. It is a paid one, and the remaining two are free. You can use them via Hugging Face library. So you can use these models to embed the chunks into some sort of numerical vectors. So what happens is after we have our chunks, we convert each chunk into a dense numerical vector using this library, and the numerical vector looks like this actually. It has some predefined length like 384 entries or 768 or 1536 entries actually. So this number depending upon the model, because these models can only be able to generate some fixed length of vectors actually. Text embedding 3 small OpenAI model is capable of writing 1536 dimension, and if we take embedding 3 large of OpenAI is capable of writing 3072 dimensions actually. This is a very accurate model, but we have to choose this particular model depending upon the need, accuracy need actually. Else it, because some models require high computational resources, because ChatGPT, except this OpenAI model, remaining all models, most of the time you may have to run them in your local, meaning you have to download that entire model and then you have to call it actually. It requires a lot of huge resources like a GPU and CPU capabilities. Okay, so depending upon the need, you choose this model. Why we need to embed these chunks is because we cannot compare the question and the chunks based on the keywords that were there in the chunks and the question actually. We have to compare these chunks and query based on their meaning, and these embedding is very useful to extract the meaning from the sentence chunks or and the query. So for example, take this chunk one. The warranty period for this product is 12 months from the date of purchase. So when you embed this, it may look something like this actually. And the second chunk, customers are eligible for repair services under certain conditions. So this chunk, when you embed this, it will look something like this. So when you use some 1536 dimensional vector, it doesn't matter actually how long or short the sentence is. It will just embed that entire chunk into this dense numerical vector. These vectors capture the essence of the sentence or the query. What happens is we will do this embedding once for these chunks, and we will do the same embedding again for the query, because when we use the same embedding model for the query and the chunk, then we can directly compare these vectors of the chunk and the query using some scoring techniques like cosine similarity, etc. Next, after we embed each chunk into this finite vectors, so then we have to store them and make it available for searching actually. And this process is possible with a database called vector database. There are many vector stores available in the literature like FAISS. This one was developed by Facebook, and this is Pinecone and VV8 Chroma. So these are all some of the popular vector stores. So in this tutorial we used FAISS. So this one was developed by Facebook, and we are using this because it's lightweight and you can do everything in your local actually. What happens in this stage is whenever a user asks a question, say like how long the warranty period is, so this query is converted into a vector like this using the same embedding model that we used above for embedding the chunks. So, and then we compute a vector similarity. Mostly we use this cosine similarity between this query vector and the chunk vectors in the database. And then it returns all the chunks that are close to the query. In this particular example, chunk 1 is very closer to the question actually, because chunk 1 is warranty is 12 months, right? So we ask her the same thing, the warranty period, what is the, how long is the warranty period? And that is very close to this first one. Warranty period is 12 months. So it returns chunk 1. That's what is happening in this stage actually. After finding not only one chunk actually, because here this is a very exact match, but in reality we don't have this kind of exact matches. So we have somewhat called closest possibilities. Like for the given query, what are the possible chunks that possibly contains the answer for this query? So those are something called a top k, most similar chunks actually. So k is some arbitrary number we can define things. So if you define 5 as means this model will return top 5 chunks that are similar to your query vector. After you find out the similar chunks, next we have to construct the prompt, the main prompt. So using your query and these chunks, this prompt has some basic anatomy. Like first we have to tell like the role of LLM here, and then we have to provide the relevant chunks as context, and then we have to give the question, the basic query that we have, and then following some instructions like this thing actually answer using only the context above. If the answer is not found in the context, say I don't know. So very straightforward, right? So like that, using these chunks and the query, we have to build up this prompt, and then we have to pass this entire prompt to the LLM. LLM wise, you can use any LLM, GPT-4, Claude, or Mr. Llama, or anything you can use it actually. So this LLM will generate an answer for this question based on these chunks, and then will return to you. This is what the overall workflow that is happening in this RAG. So overall it consists of 6 basic steps actually. First one is taking the query, chunking the documents into some pieces, and then we have to embed each chunk into some sort of numerical vector, and then we have to store all those numerical vectors into a database that is fast enough for searching and allowing similarity scoring techniques. And finally we have to write up the main prompt, and we have to give the prompt that is made up of using the context and the question to this LLM, and get the answer. That's it. These are the 6 steps actually. So in this entire tutorial, we are going to use LangChain for this purpose actually. I have given the uses of LangChain in detail here. So if you want to know more about this, please go ahead and read this actually. Basically, LangChain just act as a orchestrator that connects all moving parts in your LLM workflow. LLM workflow involves many things, right? So first you have to read the documents, embed them, storing them, retrieve, building a prompt, and sending the prompt to LLM, and retrieving the answer. So these are all the different stages, and you can handle all these stages using different objects of LangChain actually. So that's why we are using LangChain, because it is having everything. So for this project, I am importing some libraries. First is some OS library to manage system level instructions, and some path library to manage paths, and then we are calling this PyMUPDF loader. This is a LangChain document loader, and we are calling this recursive character text splitter. This splits the large documents into some manageable overlapping chunks actually. Whenever you're working on this kind of large projects, it is always good to maintain some good folder structure. For example, in this project, I have created this sort of folder structure. The primary folders are data, notebooks, API, front end, and some files in the root folder. Okay, but within the data folder, I again have some subfolders like raw PDF, chunks, files, index, or query examples like this actually, because we have to deal with some lots of data and lots of files actually when you are working in this kind of project. This raw PDFs contains the PDFs that we have in your local directory, and the chunks contains the bits and pieces of the information that was generated by the embedding model, and then FAISS index contains the vector embeddings and some query samples. And here contains our main notebooks, and then here we have this RAG API. This is our backend for this bot, and here is our front end for this bot. And here after that, I have created some two files called requirements.txt and readme file. Readme file generally have some instructions about how to understand this project, and how to reproduce this project, and such kind of information you can place it here actually. And this requirements.txt is very important. What it contains is it contains all the libraries that are used in this project. Okay, we used several libraries, right? We listed all of them here, and when you want to rerun it in your local environment, you just have to use pip install -r requirements.txt. When you run this particular statement, it will install all these libraries in the environment so that your project will run without any difficulties. So that's why I have placed a requirements.txt file. Here I'm importing these libraries, OS, pathlib, LangChain document loaders, and text splitter. Here I'm making some directory variables. So the first one is a raw folder, raw PDF directory. Second one is a chunk directory, and if the chunk directory is not available, so please create it. So this is how the directory looks actually. This is a relative path, and then here I'm defining the text splitting function. It takes the chunk size, meaning 500 characters, and a chunk overlap of 100 characters. What is this overlap is, for example, the documents, if you take for example, if you take any document, every paragraph that you see in the document is not independent actually. It is related somehow to the previous paragraph, or somewhere it is related to the after that paragraph. So meaning every text or a sentence that you see in the book is continuous in nature. So every sentence that you see builds on the previous context. So that's why while chunking out these chunks, we have to chunk based on the overlap just to make the continuity in the chunks actually. And then here I'm defining some separators. So like paragraph breaks, new line breaks, and spaces, and some individual characters like this. Okay, this is a main basic text splitting function. And then I have loaded, and then I have created this load and chunk PDF functions actually. So what this function does is it loads the PDFs. This is the two statements that loads the PDF, and this text splitter will chunk the PDFs actually. And after that, in this function, what we do is we will do all the processing. Like this is basically a function, right? We have to call it. So that's what we are doing here actually. We have created a for loop that runs on all the files in the PDF directory. So it takes each file at a time and do this loading and chunking, and then it stores all those all those chunks in this all chunks. If you look at here, these are all the 4 files in our PDF directory. So we have 4 files here, and it loaded here, and the total chunks of 4,311. Okay, these are all the total chunks that were generated from the PDFs, and then we are storing these chunks into a JSON file here actually. Why JSON file? Because it is easy to load and easy to process, because JSON file contains variables in the form of a dictionary. If you look at here, this is our JSON file. Each one is a chunk. Each entry in this JSON file is a chunk actually. So it looks like this. It has two variables mainly: page content and the metadata. Metadata means the information about this paragraph actually, from where this chunk was extracted, like the book, page number, etc. Likewise, we have some around 4,311 entries. Okay, and after we create and save these chunks into the JSON file, our next step is to embed them into numerical vectors. So that's what we are doing in this. So in this phase, we are embedding and generating the FAISS vector store. For embedding, we are using this text embedding 3 small model. So this one was obtained from OpenAI GPT. This is a paid model. If you want to use them, you have to pay some small amount of money. So these are all some of the libraries that I have taken. So let's load all of them here actually. So what it does is, this path and JSON, these two libraries are known libraries. First is to manage paths, and the second is to manage JSON files. And this third library, tick token, this tick token evaluates the total number of tokens for the given query or for the given chunk. And then this TQDM is a internal library. It adds a progress bar to any loop actually. This is just for visualization like purpose. And then this LangChain vector store FAISS. I told you about this, right? This FAISS is a Facebook vector store. It is based on similarity search. And here we are loading few more libraries from the LangChain OpenAI. This is OpenAI embeddings, and then we are loading a document, and the document is the fundamental object in LangChain. And here I am loading this text loader, and finally I am loading this load.env. This env file is generally not visible to any people. Generally you should hide it because it contains some key information like API keys, passwords, or access related data that you should not reveal to anyone, so that you have to hide here. And I'm just loading it here using this load.env function, and here I'm creating two paths, and here I'm calling this embedding model. Embedding model is text embedding 3 small. So what and how this embedding done is I have already explained. So what it does is it takes the paragraph or a query or anything, it generates a vector like this. Actually it has in total of 1536 real values. So this is based on ChatGPT one. So that's why you see 1536 values. And for different models, even in the OpenAI, you can see different number of vectors actually. So depending upon the need and the cost, you can choose this model. What happens is if you use just 3072, it consume your tokens like anything. And if you use 384 model, so it is not so accurate, but it does some work. So likewise, actually, depending upon the computational capacity and depending upon the cost you can bear, so choose this model appropriately. After we loading the embedded model, and then here I'm just loading all the chunks from the JSON file. So total overall 4311 documents loaded. And if you look at here, each chunk looks like this actually. So just we have seen it, right? So we have converted each JSON chunk into a document item just like this. Actually it has a total of 4311 entries, but just I have printed the first two here actually. And then after loading all these documents, next is we have to generate a embedding vector. So what based on similarity index. I have just explained here about how this FAISS embedding works. The same has been written here in detail. So what we basically do is we store all the vectors in a database called a vector store. So that's what it is, FAISS. So whenever we receive a query, like for example, what is the warranty period of this device, we embed this entire query into a numerical vector, and then using that numerical vector we compare the numerical vectors of all the chunks, and then we identify the top k semantically similar chunks. So these are not similar based on the keywords, these are semantically similar, meaning these chunks have similar meaning to what is asked in this query, like that. Okay, that's what we do here. One of the key important thing in this kind of projects is token counting. Actually you take any LLM, be it OpenAI LLM or Gemini or BERT or something else, it cannot take all PDF in one go. Actually you have to provide the quantity of information that the model can accept in one go. So that is what is defined by this token limiter. So here we have defined this 250k per API call. So this is the token limit of OpenAI. So this you can find out from OpenAI website. So likewise for each LLM model, there is a token limit. Even if you send text that has more tokens than this, that text will not be considered at all. It goes waste actually. So that's why we have created a function based on this tokenizer library, where we evaluate the tokens for the given chunk or given information. Actually what it does is, so for example, if you take a simple sentence like secure data in the cloud, this is your sentence. So how will you convert this sentence into the tokens? So total how many tokens it will take. So for that you have to use this tokenizer.encode.x. So if you do this, first it will convert your entire sentence into some sort of numerical values, and then based on that it will evaluate the total number of tokens. So this tokenizer divided your entire sentence into 7 tokens. So basically 1 2 3 4 5 6, and this exclamatory mark is one sentence. It is not the case in every time actually. Sometimes if you have some strong words like embedding, so what this tokenizer will divide that embedding into two words, and that will be counted as two tokens. So like that. These are all the token limits for GPT-5. GPT 3.5 you can go up to maximum 16385. GPT-4 you can go up to 8192. GPT-4 Turbo you can go for 128,000. 1000. The other models like text embedding 3 small, text embedding 3 large, these are the tokens for this. These are all OpenAI models. If you go with other models like Mistral 7B, Llama, Mistral 8x7B, these are all the maximum tokens that are available for this, of which some are main LLM models, some are embedding models. Each one have their own token limit. Okay, keep that in mind before before using your LLM model or the embedding model. And next, once we evaluate the tokens, what we do is we will call all the above functions that we have created before in this entire thing. So what we do is we load all the documents. So documents are basically the chunks in this LangChain document object. So each document represents one chunk in the LangChain. So what it does is, so we totally stack up all the chunks until it reaches the token limit. So for example, if the first chunk covers only 1000 chunks and 1000 tokens, and the second chunk covers 2000 tokens, so overall we have covered 3000 tokens. So likewise, we batch all the chunks until we reach the token limit. Once we have this once we reach this token limit, we send that entire chunk information into the embedding library in one go, and then we get the vectors. So like that we do actually. So if you look at here, we have a total of 4311 documents, and all of it are embedded. And one small step is needed. We call this final batch. What happens is, after the loop ends, this block checks if there is any remaining data in the current batch that has not been embedded yet. If anything is missing in the above loop, it will take all those batches and embed here actually. Once we have done all the embeddings, so here I have printed something like the first document content and its metadata. Just for demonstration purpose, I have printed here actually, and then also for easy looking how the embedding happens actually. This is your first document content, right? So this is your first page content. So the vector index for that looks like this. So here I have just printed some 1600 dimensions, but the vector length is 1536 only. So it just print the 1536 element and does not consider this elements after the 1536. You can print a smaller version of this just to view how it looks like actually. So this is your vector for this particular page content. After that, what is happening is I'm just saving all the page content vectors and the metadata into this data FAISS index OpenAI directory actually. So if you look at here, if you go into data and if you go into FAISS index, you see this directory OpenAI, and within that you see these two files, index.faiss and index.pickle. These are two important files that has the information about the metadata and the vector embeddings. So we load these vector embeddings and the metadata in this notebook to retrieve the answer for our question actually. So far we have completed two phases. First is loading the PDFs and chunking them into small manageable chunks, and then we embedded them into numerical vectors and we stored them in a vector store. Okay, now in this phase 3, the final phase, we are loading all the chunks into our RAM basically, and then we find out the relevant top chunks for the given query. Okay, here we are loading up these libraries. So these libraries are some important libraries. Like first one, we store FAISS just to load and read the vector embedding, and then this OpenAI embeddings library, and then these three are important: stuff document chain, LLM chain, and retrieval QA for processing this entire chain of elements actually. So what this does is these are used to build this entire RAG pipeline. We will see them in action shortly. And the next one is a prompt template. So using this we built the entire prompt, and then we are importing this chart OpenAI library, and then we are importing this JSON and .env. Don't worry about what these libraries does. We will see each one of them action shortly. Here I am loading this .env file. This is a very important file, just I told you, because this contains some API keys using which all of this OpenAI modules are working actually. Here I am defining this index path, so the location in which our FAISS and index.pickle files are located. So what we are doing is we are just loading all the files into our memory. We are using the same model here to load and interpret this. Okay, the same model using which we embed the chunks into numerical vectors. So here we are calling this, we are defining this retriever object. So here I am mentioning K2, meaning we are just interested in two top relevant chunks actually. You can choose any number, and then after retrieving this vector store, we are just building the main brain with the custom prompt. So our prompt follows some structure actually. What the structure is, so first we will just tell some information to the LLM like how it should behave, and what kind of instructions it has to follow. Like it should not make up any answer, right? It has to give some exact answer that is available in the PDFs. If it does not find any relevant chunks, it should just say, I don't know. That's what we are giving the instructions here. And then the context. Context represents the top K chunks that were retrieved from the PDFs, and then our main question and the answer. And this answer has to be found by the LLM. This is our main prompt template. Once we define this prompt template, we set up the language model here. We are using this GPT 3.5 turbo, and here we are setting the temperature is equals to 0. You know what this temperature does? This temperature defines the creativity levels of this LLM actually. It varies between 0 and 1. If the temperature is 1, it will go highly creative, meaning it never say I don't know. It will always try to make up some answer for you. Sometimes it make up new facts actually. So and these facts sometimes look very real, so that kind of creativity levels it can show. But if you put 0, it doesn't show any creativity. If it is available, it will just give you the answer. If it is not available, it will just say I don't know. That's what. And then we are building this LLM chain. This LLM chain wraps this LLM with the prompt. So that's what we are doing here actually. And then we are preparing the chain that combine the documents. This tells the LangChain how to combine multiple chunks into single context block. This is important, right? So here when we are loading from the vector database, we get different number of chunks, and we have to combine all those chunks into one single context block to feed to the LLM. And then we are return this retrieval QHN. Basically this finds the answer for it actually. So this is where we are creating the prompt template, and here I am setting up the LLM, and then here I am combining the LLM with the prompt, and then here I am creating this document chain. So what it does is it creates the context by combining all the chunks into one unified context. And this is our final retrieval QA. As I said, this is very important because it combines all the things like retrieving, fetching up the top K documents, building up the context from the individual chunks, and then combining with the LLM and prompt. So like that, we will do all those important activities here actually. And then we take up the query. Query is simple. What is the difference between PMF and CDF? PMF means probability mass function, and CDF means cumulative distribution function. So these two definitions are available in the textbook that we have stored in the raw PDF. So basically we are expecting the definitions of it, and here we are doing this chunks actually, the relevant, finding the relevant chunks, and then generating the context, and then we are building up the final prompt. So if you look at what the final prompt looks like, so here I have added some print statement to show how this prompt look like. This is our final prompt look like, which is what we are sending to the LLM. So this prompt has some generic instructions, and then the main context within these symbols, and then we have a question and an expected answer. So this we are expecting, that is empty, so LLM has to give that. And here we are calling this QA chain invoke with a query, and this gives the response, and that we are printing here. And the answer that we received from the LLM is the main difference between a PMF and the CDF is that, so this is the answer that we have got from the book. And from which book? So this is the book actually. From this book we have got that answer. Okay, so this is what Ragbot does is, okay, it will go through this entire workflow and generate the answer for any question that you asked actually. If the answer is available in the PDFs, it will give you one. If the answer is not available, it will just say you I don't know. Here I have given the functionalities of LangChain. So please go through this if you want and gain more understanding about how LangChain helps in building this RAG bots. Actually, this LangChain is a very important library now in developing this RAG bot assistant. So in future, if you want to develop agentic AI tools, then at the time also this LangChain, LangGraph, these are all very important tools. So you have to learn these tools in order to develop this kind of RAG applications. There is no second negotiation, and there is no other library that is more capable of LangChain for this kind of purposes. Actually, after we build up this thing, so I have created a small interface like this. This is a web interface. So here is the backend. So whatever the code that I have written here, I have just reproduced everything again here and created this backend. Just whatever the data that I generated by embedding the chunks into the vector stores. So that I'm loading here and then passing the question via this question form and then this button. Everything we have it here actually. So and this is the front end that I have created. So this is the front end. So it's a small thing. So it looks like this actually. So in order to run this, you have to run this small command like uvicon ragapi.app double double reload. You have to run this. So when you run this, what happens is this will run the backend, this code. After you run this backend, then you have to open this index.html. You just have to double click like this. It will just show up here. So I'm just closing the earlier one. So you can ask some questions like what is CDF. It will just take a while to think and it will answer based on the information that is available in the documents. Actually, CDF stands for cumulative distribution function. If it is a function that gives the probability that a random value takes, something like this. Actually, you can ask some questions like what is PMF. Will take a while and it will give you the answer. You can also like ask something like what is the difference between PMF, CDF and PMF. Yeah, that's it. It will give you some answer, and along with that it will give you some sources as well. For example, you take up this source, so you go to page 81 of this source. So this is Alan B Downey, page 81. So go to this data raw PDFs and Alan B Downey, page 81. Get this. So this is a 40 and this is our page 81. What else are the references? It has page 81, 82 and page 8. So these are all the three main pages, 81, 82 and 8. Actually, you just take a look at it here. Actually, 81 we don't have any information that is similar to CMF or PDF, sorry, PMF or CDF, but in 82 we have some information like PMF, CDFs and all. So yeah, this context we have some information. Actually, maybe while we are chunking into different chunks, some text might have been overlapped, but we have relevant information in this 82 and 83 pages. So this PMF and CDFs are good, and this one is appropriately derived, and this answer is appropriately derived from this information. Actually, so that's how this entire bot works, and this bot is very central and becoming very popular these days in many enterprise applications. Actually, if you take up any public library or research libraries, like for example if you take any Elsevier or Springer. So this is all about these tutorials. If you have any questions or need more clarifications, please feel free to comment in the comment section. See you in the next tutorial. Thank you.